sp3d. It's going to be sp3d. It's going to have this trigonal bipyramidal structure. And it's going to have 5 sp3d, sp3 sigma bonds. And so phosphorus, 1, 2, 3, 4, 5, sp3d. We're going to have 1 electron in each of those, and then 5 chlorines can come in and bond to that. Well, if we're at sp3d, what is the percent d character of each of these orbitals? Well, the sp3d is 1 part s, 3 parts p, 1 part d, so a total of 5 parts. So 1 out of 5 parts is 20%. And so this is 20% d character in each of those hybrid orbitals. Well, this is with the expanded octet. However, if there's not much d character in there, then what is the bonding? That is, if we don't have any d, how can we accommodate that many electrons? We can't accommodate that many electrons. In fact, we can only accommodate if we just use the orbitals on phosphorus. The normal orbitals on phosphorus are this. The s and the p, 3s and 3p. And so we got 4 orbitals. Those 4 orbitals can hold a maximum of 8 electrons. And so alternatively, if we make only 4 bonds, like this, I'm going to ignore the lone pairs. That's going to leave phosphorus short, and then we're going to have 1 more chlorine here. And this 1 more chlorine, we're going to ionically bond it. And so this way we don't have to expand the octet. And so if I do that, here, I can bond 4 chlorines on a positive phosphorus, ionically bonds the 5th chlorine. Well, it results in resonance forms, and in this case the resonance forms depends on where I have the ionic bond. And so one of the resonance forms is I could put the ionic bond in this axial position rather than that equatorial position. And then I'll put the 4 chlorines here, 3 of them in the equatorial and 1 in the axial. So we'd have something like this. And so what I can do is I can rotate this ionic bond to each of the 5 positions. And so I'm going to get 5 resonance forms for this. And so when I think about it, 1 out of the 5 bonds is ionic. And so this is 20% ionic. And in fact, the actual structure will be a hybrid. And the bond in the hybrid, all 5 bonds would be equivalent. And each of those bonds would be 20% ionic. And so what we have here is we have this range. The range is we can have full d orbital, participation or hybridization. In this case, we aren't using unhybridized. We're actually hybridizing the d orbitals into the hybrid. So each of these orbitals is 20% d character. Or we could have 0% d. This is 0% d character because there's no d electrons here. I hesitate to call this sp3 because of the geometry. The geometry is not quite right. It's going to be some other mix. And so here, the hybrid is going to be 20% ionic with 0% d. And so we go from 0% ionic to 20% ionic, or 20% d to 0% d. Where's the reality? The reality is somewhere in between. And that reality we can figure out based on calculations or whatever else. And this is what it's going to look like. Actually, this is SF6. SF6 would be sp3d2. So if we don't expand the octet, we get 4 fluorines covalently bound, and then the other 2 fluorines will have to be ionically bound. Again, we'll generate resonance forms. We'll come up with a hybrid. Hybrid's going to be some percentage. Or we could expand the octet. If we expand the octet, we get 6 sp3d2 orbitals, forming sp3d2 sp3 sigma bond. So we either get hyperconjugation or hypervalent. This is hypervalent. It's got a bigger valence shell. This is hyperconjugation here. Well, compared to quantum mechanical calculations, the sulfur has a charge of plus 3.17. The fluorine's at minus 0.53. The expanded octet is questionable since wave function calculations show very little contribution from d orbitals. So it's looking like this is perhaps more accurate. But this is hard to visualize because we need the hybrid structure. But we don't have to do any of this if we use quantum mechanics. So, question is this: why do we have 2 bond theories? Isn't there just one bond? If there's only one bond, shouldn't we just have one bonding theory? Oh yeah. Problem is you can't draw it. You're right. You can't draw it because things will start to get more and more complicated. Yeah. Well, we can draw some of the simpler ones. So let's draw some of the simpler ones. And so what we're going to do is we're going to go to this. Nice. Molecular orbital theory. Molecular orbital theory is the, what did I call it compared to valence bond? Yeah. Valence bond is quantum mechanics too. Both theories use orbitals. So what's the difference between valence bond and molecular orbital?
Molecular already gives you the hybrid.
Yeah, molecular is going to just take us to the hybrid, whatever that structure is going to look like. It'll give us the ultimate structure here, whereas we were kind of guessing with the valence bond for some of them. What else? They describe bonds differently. Did I mention this? Valence bond describes a bond as overlapping atomic orbitals, whereas molecular orbital theory describes a bond as electron density, right? Excess electron density, bonding MOs. The reason why we have 2 is because one, although not as accurate and not as informative, is much easier than the other. The other is much more accurate, much more informative, but it's much harder. So which was which?
This is molecular.
Yeah, molecular orbital theory. This is, what did I call this? I called this the quantum mechanics full version, and valence bond was the quantum mechanics light version. And so if somebody asks you, why do you need 2 theories to describe a bond, what would you tell them?
Because together they form a figure.
No. MO would form a big picture. Valence bond is kind of a blurry picture with some errors. Easy to visualize. Easy to use. Well, anyway, let's talk about MO theory next, molecular orbital theory. MO theory, we have atomic orbitals, which we talked about, the S, the P, the sp3, sp2, whatever. Those are atomic orbitals. Molecular orbitals are a whole new set of orbitals, and these orbitals are big. They encompass the entire molecule, however many atoms are in that molecule. And so let's look at the molecular orbitals for fluorine, F2. If we look at the molecular orbitals for fluorine, this is how we generate the molecular orbitals. We generate them by doing an LCAO. LCAO stands for linear combination of atomic orbitals. And so psi1 here is a molecular orbital, which is equal to phi1, which is an atomic orbital, plus phi2. So we have this constructive combination. We also have this destructive combination, the phi1 minus the phi2. And so whenever we add two atomic orbitals, we generate two molecular orbitals, depending on how we add them here, one way and the other way. We have to consider both ways. When we do this here, we end up with a bonding molecular orbital. When we do this here, we end up with the anti-bonding molecular orbital. We'll talk about those. Each MO can be represented mathematically as a linear combination of AOs. That's it. This is the math. The total number of MOs is equal to the total number of AOs. And so if I have two atomic orbitals, I'm going to form two molecular orbitals. So if I have phi1 and phi2, I'm going to form psi1 and psi2. The MOs can be classified as bonding, anti-bonding, or non-bonding. Non-bonding are just your AOs. They aren't doing any LCAO linear combination. The electron configuration for the molecules obtained just like you would for atomic orbitals. You just place molecular orbitals, even though they're bigger, they only hold 2 electrons. And so let's look at the LCAO here first. Actually, before we get to fluorine, let's do something simpler. Hydrogen. Hydrogen has a 1s orbital here on one hydrogen A, and if we look at hydrogen B, 1s orbital. Now we do the LCAO. LCAOs will do this constructive here, which results in this. This is one orbital. This one orbital is big because here's the nucleus, here's the nucleus. We call this a bonding orbital. In fact, we give it a name. We call it the sigma 1s bonding orbital. If we look at the wave functions here, you can see there's constructive position here. However, if we do this, that is, if we do positive and negative amplitude here, then we're going to get destructive interference. In fact, we get a node here. You look at the node, there's a node, that means the two nuclei see each other and they're going to repel. Here we have pretty good electron density between the two nuclei. They're going to attract the nuclei. And so this is going to be more stable, lower in energy. That's what we see here. So here we have the 1s orbital on hydrogen A, the 1s orbital on hydrogen B. We form the sigma 1s here, and the sigma star 1s. Now H2 is going to have 2 electrons, one from this, one from that. So we'll just fill this as normal. An MO can only hold 2 electrons of opposite spin. And so this fills it here. So we only have electron density in the bonding MO here. We can get something called the bond order. The bond order is the number of bonding electrons minus the number of anti-bonding electrons. And so in this case, we have 2 bonding electrons, no anti-bonding electrons. So if we have 2 electrons, that's considered one bond. 2 minus 0 divided by 2. And so this is bond order 1 or a single bond. We can also get the magnetic properties here. And so let's take a look at this. There are a whole bunch of diagrams here, but this is hydrogen, what we just talked about. Hydrogen is going to have 2 electrons here in the sigma 1s bonding MO. The bond order is going to be 1. If we tried to bond 2 heliums together, take a look, He2. Each helium has 2 electrons, so a total of 2 times 2 is 4 electrons. So we put 2 in the bonding, and then the next electron has to go in the anti-bonding. And the 4th electron will go in the anti-bonding. And so in this case, the anti-bonding cancels out the bonding. And so we got 2 minus 2 divided by 2 is 0. The bond order is 0. In other words, if we have electron density here, they cancel each other out. And we get no bond formed. However, we can look at some exotic species. So if we take H2 and knock an electron off, we'll form the H2 plus ion. If we look at the H2 plus ion, that has 1 electron. And 1 electron is going to give us a bond order of 1/2. And so this should form. It's going to have a weak bond, but it should be stable enough to form it. Interestingly, He2 plus should form as well, whereas He2 does not. He2 plus will have some bonding interaction because we have more electrons in the bonding MO, the sigma 1s, than the anti-bonding. And so we're going to have net bonding occur. And the bond order is 1/2 here for He2 with plus occur. All right, for second period elements, we have more orbitals. So now for second period, what we're going to do is we're going to look at the 2s and the 2p. This is a figure from the book. So when we go to the second period, we have the 1s, this is atom A, 1s, and then the 2s, and the 2p, so we'll write like this. Okay, we're going to ignore the 1s, the core, and we're just going to focus on the valence here. And so what I'm going to do is I'm going to do LCAO. And so that's atom A, this is atom B. Say fluorine A, fluorine B. So this is 2s here, and then 2p. Like this. Now when we do the LCAO, we're going to do this constructive and the destructive. And so here, if we have positive and positive amplitude, we're going to get the sigma 2s. The sigma 2s looks like the sigma 1s, but just bigger. We have a node in there, which I'm not going to show. And then, if we do the positive and negative, we're going to get the sigma star 2s. The sigma star 2s is the lobes appear to repel each other, and we end up with a node here. The node's going to be that would be the sigma 2s star. Let me just write this out. So these are core. We're just going to kind of ignore these here. These aren't drawn so accurately. So ignore this. When we're in the second period, we're just going to look at the valence. And so what I just drew this sigma 2s, this kind of cigar shape. And then I drew this sigma star 2s. The star 2s is going to have the node here. This is the positive and negative amplitude. They interact destructively. Okay, this should be symmetric. We have conservation of energy, first law of thermodynamics, so this drops as much as this gets raised, but I should have left myself a little room here, so it should be a little higher, or the other one should be a little higher. Okay, let's look at the next orbital here. The next orbital is going to be the sigma 2p. Take a look at that. The way the sigma 2p forms is like this. Look at this one here. Normally we call this a px, but they call it pz. We'll just call it z here, pz. And so we take this blue lobe on atom A, and then this blue lobe on atom B, and we get this constructive. Do you see the constructive here? And so we'll do it here. So normally I like to call this a px. We'll call this a px here. And when we do that, we're going to have these two lobes add to each other, and these two lobes shrink. So this is a sigma 2p here. If we do that, then we're also going to have the destructive case, where we have blue and red. Do you see the blue and red? If there's a blue and red, then those aren't going to add. In fact, there's going to be a node here. This is anti-bonding. Anti-bonding because no electron base. And so that's going to be raised in energy. And so if this is the nuclei, then this lobe shrinks and this lobe grows. This is a sigma star 2p. Again, there's a node here down the middle. And so these two nuclei essentially see each other. My diagram's not symmetric. It should be symmetric. All right, we have two other p orbitals too. So let's look at this one. The py and the py. So if we take a py like this, then we're going to form this. When we look at this orbital is not going to be called sigma. This one's going to be called pi 2p. It's a pi 2p because if I look at the internuclear axis, the electron density is outside the internuclear axis here. Whereas if I look at the internuclear axis here, the electron density is within the internuclear axis. And so this is a sigma, this would be a pi. Okay, this is not to be confused with sigma and pi bonds in valence bond theory. These are sigma and pi orbitals in MO theory. Okay, now if I form a bonding, I have to also form an antibonding. And so the antibonding is going to look like this, where the four lobes kind of repel each other, rather than the four lobes combining like this. And so if the four lobes repel each other, it looks like this. You have two lobes here, two lobes here. And then I'm going to have a node down the center here. And so this is the pi star 2p. Now this is what we call the side view. There's another 2p orbital projecting straight out and straight in. What would be this one here? And so what that's going to lead to is it's going to lead to a lobe that sticks out of the board. So to show it sticking out, I'll just shade it. And a lobe sticking into the board like this. And so it'd just be this one rotated 90 degrees. So if we take this one rotated 90 degrees, then we get this one here. You know, one lobe sticks out of the plane, the other lobe sticks in the plane. Yeah. And then we're also going to generate the antibonding here. The antibonding is going to have four lobes. Two of the lobes will stick out both sides, and two lobes stick in. Yes. And again, there's going to be a node here. And both of these are pi 2p's. Both of them are going to have the same energy, pi star 2p. This is a pi 2p. And so this is what we call the MO diagram, or energy level diagram for the molecular orbitals. So MO diagram. We generate from the linear combination of atomic orbitals. And so what does that look like in terms of the orbitals? This is it. So we have the sigma 2s. Sigma 2f, sigma star 2s, sigma 2p, sigma star 2p here. And then here's the pi, one of the pi 2p's, and then rotated 90 degrees. Here's the other pi 2p. Here's the pi star 2p, rotated. Actually, these two belong with each other. And so this is the bonding pi, this is the anti-bonding pi. And these two belong to each other because here we have the four lobes. Two of the lobes are sticking out, two are sticking in. These are color-coded. We aren't going to color-code ours. right, so when we generate these orbitals, these are the orbitals that we're going to have for a second period diatomic. So we're going to have atom A and atom B. So diatomic, 2 atoms in the second period. So sigma 2s, sigma star, sigma 2p, pi 2p's, pi star 2p's, sigma star 2p's. And so here's our diagram. Sometimes it helps to have the AOs in here and then do the LCAO. This is the LCAO. Figure it out. Okay. Now, what's weird about this one? Take a look at what's weird. Something weird about this. Look at the diagram you have just drawn, and then this one, and that one.
Yeah, the highs, the antibond for 2p's are lower energy than for the sigma.
Sigma star?
Yeah, for sigma star.
Well, actually, that's the case up here.
Oh, it is.
Yeah, sigma star, then pi star. Do you see what's different? What's different is this. This orbital here, the sigma 2pz. The sigma 2pz is higher in energy, but got bumped up higher in energy. And so we end up with 2 diagrams here. This is the normal diagram, and then we have the abnormal diagram. So this is normal. In the normal diagram, it's going to go like this. Sigma 2s, sigma star 2s, sigma 2p. Sigmas are lower in energy. They're lower in energy because they got more electron density directly in the internuclear axis region. Followed by your pi 2p. These are the same energy. Followed by your pi star 2p's. Pi star. Followed by your sigma star 2p. Okay, the 2p orbitals, do you see the symmetry? 3 of them below here, 3 of them above, standard. And the 2s, the symmetry here. So this is what we call the normal. The abnormal, what happened to the abnormal is the this. Sigma 2s, sigma star 2s. And then we expect this sigma 2p, but the sigma 2p got bumped up in energy. And so the next orbitals are the pi 2p's. The pi 2p, pi 2p, and then finally the sigma 2p, and then the pi stars 2p, pi star 2p, pi star 2p, and then finally the sigma star 2p. And so why did this orbital get bumped up here? And so this is abnormal because of repulsions. It turns out the repulsions become more significant at lower z's than higher z. And so we use this one, the normal, for z greater than or equal to 8. We use this one if z is less than or equal to 7. And so it depends on the z. And so what is the repulsion between? The repulsion is going to be between take a look at these 2 bonding orbitals here. If I look at the sigma 2s and the sigma 2p, do you see they occupy pretty much the same volume? There's the nuclei here. And so what happens is at lower Z, I get something like this. Here's atom A, here's atom B. If I look at the sigma 2s, the sigma 2s is like this. If I look at the sigma 2p, the sigma 2p is like this. Now, if I look at the electron cloud, basically they're occupying the same space. So I get electron-electron repulsion between the sigma 2p and the sigma 2s. Essentially, they're in the same volume. That's with lower Z. With higher Z, the greater the Z, the more the orbitals get pulled in, and the smaller they get. And so with a higher Z, Z greater than or equal to 8, then what we see is this. Which orbital is more penetrating, an S or a P? An S or a P? S. S orbital is more penetrating. S orbital is more penetrating, so the S orbital is going to get pulled in more than the P. And so at higher Z's, what happens is the sigma 2s shrinks down more than the sigma 2p. And so even though a large part of the volume is the same, the sigma 2p has more breathing room here. If you look, this area does not overlap, or this volume does not overlap here. And so here we'd have like 4 electrons in a 1-bedroom apartment. Here we'd have 4 electrons in like a 2-bedroom apartment. And so you have this extra space here. And it's because the sigma 2s gets pulled in more than the sigma 2p, whereas here, because Z's smaller, shielding and penetration is significant. And so what that means is you have to remember 2 diagrams. And so let's use these. Here are the 2 diagrams. Is this the normal or the abnormal? This one. Abnormal. You see the sigma 2p's up here? That's because Z is low. Z is low, the 2 orbitals are pretty much occupying the same volume. So this is diatomic lithium, the Li2 molecule. Can you make Li2? Would you expect it to exist? Yes. That's because Li2 should have a bond order 1. There should be a single bond. That is, we have 2 electrons in a bonding MO, and it should be diamagnetic. How about Be2? If I try to make diatomic beryllium, it wouldn't exist. It wouldn't exist because we put 2 electrons in the bonding, 2 electrons in the anti-bonding. They would cancel each other out, and we get no bond formation. So Be2 does not exist. B2 does exist, diatomic boron. Diatomic boron would be, we'd have 2, 3, 4 bonding electrons minus 2 antibonding. And so if I have 4 bonding minus 2 antibonding, that gives me a bond order 1, single bond. So it should be paramagnetic. Diatomic carbon should exist. It would have a double bond or bond order 2. That is 2, 4, 6 bonding electrons, 2 antibonding electrons. It would be diamagnetic. Nitrogen. Nitrogen would have 2, 4, 6, 8 bonding electrons minus 2 antibonding gives us 6 divided by 2 electrons per bond gives us 3 bonds, equivalent to 3 bonds. And it's diamagnetic. And so nitrogen should triple bond. We go to oxygen. Oxygen is 2, 4, 6, 8 minus 4 gives us a double bond. And it's paramagnetic. Well, this is different because if we do valence bond theory for oxygen, we get diamagnetic, not paramagnetic. So which one's right? Well, paramagnetic's right because if you pour, this is liquid oxygen. If you pour liquid oxygen into a magnetic field, it gets trapped. You see the oxygen's trapped with a magnetic field, so it doesn't drop. due to gravity there. And so oxygen is indeed paramagnetic. There, and you can see. Come on. Just want to zoom in here without changing the slide. Okay, fluorine, single bond, diamagnetic. Neon, any two you wouldn't be able to form. Equal number of bonding and anti-bonding. The bonding cancels itself out. These are called homonuclear diatomics. This is C2. This is just showing that this can be verified. This abnormal diagram here can be verified because if you did C2 with the normal diagram, it should come out paramagnetic. But if you do C2 with the abnormal diagram, it comes out diamagnetic. Well, C2 is diamagnetic. It's weakly repelled by magnetic fields, not attracted. So that's correct. Now, if we do heteronuclear diatomics, we have to pay attention. The higher the Z, the smaller the orbitals, and the lower the energy. So neon has the highest Z, the smallest orbital. Boron has the lowest Z, bigger orbitals. But that's for the 2s. The 2s more penetrating, so we see this effect more profoundly. The 2p's are less penetrating, so there isn't as huge of a drop in terms of energy and size for the 2p's. And so the two S's, the sigma 2s is going to get pulled in a lot more than the sigma 2p's. But what this is going to mean for us is carbon versus oxygen. Oxygen is more electronegative, so it's going to pull the orbitals in, and they're going to be lower in energy and smaller. And so this is heteronuclear. This is carbon monoxide. If you look at carbon monoxide, and you don't have to worry about this in nomenclature, 3 sigma, 4 sigma, 1 pi, 5. This is, there are a lot of MOs that get generated. And so this is what's the naming system for these MOs. You can see some of these MOs look kind of bizarre. Look at the 6 sigma MO. Is that weird or what? Or even the 2 pi MOs. Those kind of look weird. Yeah. This is for carbon monoxide. And so here's the MO diagram. Now, is the MO diagram a normal or abnormal? When you look at this, well, oxygen should be a normal. Carbon should be abnormal. And so which one won? The abnormal. Which is weird because I would have thought oxygen would win. And so we just do the normal MO. But do you see how this sigma is above the pi's? It's abnormal. Carbon 1. And then we just fill it out. Carbon has 4 valence electrons, oxygen has 6. That gives us 10 electrons. 2, 4, 6, 8, 10. We fill it using Hund's rule and all the other rules. This gives us 2, 4, 6, 8 bonding minus 2 anti-bonding gives us 6, the bond order of 3. So carbon monoxide should have a triple bond. All right, here's an application of MO theory in benzene. We did valence bond. This is a valence bond showing the sigma bonds. This is a valence bond showing the pi bonds. We could also do MO. This is valence bond here. This is MO. And so we generate these MOs. This is one orbital. If you look at this one orbital, the electrons, the pi electrons here are delocalized throughout the entire molecule. And these are some of the other MOs. These are bonding. There's some anti-bonding MOs here. Here's ozone. For ozone, when we did valence bond, we had a double bond and a single bond. So we had this, but we had the hybrid. But when we do valence bond, we just look at one of the resonance forms and go from there. This is the MO, totally delocalized here. So some more MOs of ozone. Here we have these aromatic systems, these alternating single and double bonds, beta carotene, lycopene. These often are colored, because what happens is you got a lot of MOs. You generate a lot of MOs and you come up with something called the HOMO and the LUMO. HOMO stands for highest occupied MO. LUMO stands for lowest unoccupied MO. And there's an energy gap there. And so we can promote an electron. Oftentimes promoting an electron here, especially if we got a lot of MOs like this, is small in the visible range. And so a lot of these things are colored, like beta carotene. Beta carotene has color to it. And so here's the MO energy level diagram as we add additional carbons. We got 16 carbons in that structure. Okay, and then we talked about this. This is MO here. This comes from MO theory. Not valence bond. MO. Look, this SCl2, look, those bonds are the same. This is sulfuric acid using MO and sulfate using MO. Here we have the different structures. There, this is sulfuric acid here. This is sulfate. One structure is missing for sulfate, but this is the two extremes. The one structure I would have had in the middle here is 1 PD pi bond versus 2. So it'll be in this range here. This is going from ionic to expanded octet. So here we have 2 unhybridized d orbitals participating. Here we have 0 d orbitals participating. It's sulfate. End of chapter. Okay, so what I want you to do right now is this. I want you to do oxygen. I want you to do the valence bond and the MO analysis of oxygen, and then I'll come by and